Welcome back to our next video on projection at an angle. We're continuing with our Queensland physics syllabus, talking about the motion of objects in Earth's gravitational field. All right, let's get us thinking about a few questions here. First question there about has the design of javelins changed? There's a bit of truth in that one. I encourage you to go and have a look at that and see if you can understand exactly what went on there. Similar with Alan Shepard as an astronaut on the moon in 1971. Did he actually go up there and play golf? It's an interesting story about how honest he was with NASA about what was going on there prior to them leaving Earth on that mission. As we said last episode, we've been through most of our curriculum objectives there, but we're going to really explore the last two in this particular story today. So, what do I mean by that? Looking at horizontal and vertical components of vectors of velocity. Have a look at how the horizontal and vertical components are independent of each other, so we can resolve the object of motion, resolve the motion of objects. Rightio, so when we consider an object moving, we say it moves as a parabola because it's like when you're projecting an object up at an angle, it will go in that parabola sort of shape. We often look at equations like this one that's listed here, where we're breaking that into the y components of the vertical displacement, where the object moves up and back down. We say that the path of this parabola varies according to time squared because we have a time squared there. So it's like if I just take my variables, these one here, sy is proportional to time squared. We relate the vertical components to the horizontal components using the time because the time carries over into our horizontal equation. That's the horizontal range, which is Sx, equals the initial velocity in the x direction, just the x component of it, multiplied by the time. And as we saw last episode, that's just basically a rearrangement of speed equals distance over time, where I'm replacing distance with displacement and speed with velocity. So we spoke about this one before. The displacement in the x direction is called the range. It's how fast an object moves horizontally during this projection. Now, today what we specifically want to look about in projectile motion is the three that are shown in our little diagram there. Where we want to look at objects that are projected and they land at the same height that they are projected at. So you throw an object and it lands back down on the ground that you're standing on. Landing at a lower height, that's the examples where we looked at, say, throwing a rock off a cliff, that sort of thing. Where the rock ends up is at a lower height than where you are. And we want to look at landing at a higher height. So we'll look at the example there where you throw something up onto a higher platform or something. Maybe you're throwing something up onto a shelf. Perhaps you're throwing a basketball up into the hoop and you're interested in your height that you're starting at and the height that the hoop is at where the ball's got to end up. If we think about our little blue bubble there, what can we determine? Well, in this scenario, landing at the same height, the displacement won't change. You'll have a horizontal displacement, but the vertical displacement is zero because you end up at the same height that you start at. In that scenario, g is always negative 9.8. If we look at landing at a lower height, then obviously there's going to be a component of vertical displacement and it'll be a negative value because it's below where you're standing. In that scenario, the object has time to continue to accelerate down past you, so your velocity in the y direction will be bigger than the initial velocity. And the opposite's true when you're landing at a higher height. Your final velocity in the y direction is less because it goes up, stops, comes back down, but hasn't got enough time to accelerate back to where you're starting, so that y velocity is less than what you started with. Okay, let's have a look at case one. And you can see up the top right corner there, we're following our little flow chart and we're specifically looking at landing at the same height that an object was launched at. So, in this scenario, my first dot point there, impact speed equals launch speed, what we're really saying there is we know in the x direction there is no acceleration, so that doesn't change all through the entire motion, and the size of those two vectors are the same. In the y direction though, the impact velocity in the y direction is the same as what you started off as your initial velocity, but it's just going to be the opposite way. What I mean by that is uy, so the y component of the initial velocity is there as an arrow pointing up, and over this side it's the same magnitude of arrow pointing back down. You can see that the velocity in the y direction slowly decreases until it ends up as 0 at the top here, and then continues to increase as the object has time to accelerate all the way back down to our impact point, which is where we started. So Vy ends up equaling Uy, which is what I've set up there, just in the opposite direction, hence the negative. Let's look at an example. Bullets fired from a rifle at 200 meters per second. It's quite a slow bullet, to be honest. Most of your military type weapons, it's usually a good 800 odd meters a second, give or take. Although having said that, in the real world, we have to account for air resistance, so the bullet does tend to slow down quite quickly. Particularly when it comes out of the end of the rifle, it's not traveling as a nice, neat sort of shape like that. The bullet tends to tumble and tends to take up to 100 meters to stabilize and start flying normally, like the diagram I've just drawn there. Anyway, bullet was fired from a rifle at 200 meters per second. So that is U, my initial velocity, at an angle of 40 degrees. That's my angle. Let's ignore air resistance and assume it doesn't exist. What are we got to find? Vertical and horizontal components. So we've done that last time. You should immediately think, what are my formulas for that? U sine theta and U cos theta is those two components. The maximum height reached is Sy, my vertical component there of the displacement. That means that if I'm going off like this at 40 degrees, how high up does it get there? That's my Sy. Time of flight, always important to find the time of flight because it helps us relate X components and Y components together. And the horizontal range. So what is Sx? So obviously we need to find the time in order to go from Y components to X components. Righto, let's run through that. So this particular question is telling us to calculate. So as we've said, calculate, what does it mean? It means basically work something out. Think mathematically, you've got to solve something. Writing down what our unknowns are is always going to really help us. So we sort of clarify our thinking, and then we start to write down what is it that we need to find out, which we sort of specified on the previous slide. The first question was breaking it into vertical and horizontal components. So there's my U sine theta and my U cos theta to give us my Y component and my X component. Notice the vector notation required for the Y orientation there. It's going up, and I suppose if you wanted to do it for the X component, you would say to the right, perhaps, whatever you've determined. But that's stuff we've done in the last episode. Simply substitute your numbers in. We know it started at 200 meters a second, so that goes straight in for U. We know the angle's 40, that goes straight in for theta. Put it in your calculator, it all comes out in the wash. The vertical component's 129 meters per second. It's positive, so it's up. And the horizontal component is 153 meters per second. Done. Righto, part B. Maximum height reached, so that is the displacement. So we need a formula that's got displacement in it. We know all of these things. We know this now. We know this now. We need to find S, vertical displacement. Look at all those components. Go to your formula book, your data book that's got your formulas listed, and literally just pick off the one that's got all the variables that you need. So in this case, we've got v squared equals u squared plus 2gs. We know the y components, which we can substitute straight in, and we're just solving for s. Noting, of course, that gravity is acting down, so your gravity is a negative 9.8. This little rearrangement from here to here is just middle school maths to isolate the displacement. The next step down there is your mathematical working, where you're literally substituting the numbers that you know. And then the last bit is what your calculator told you when it all came out in the wash to give you your answer. This particular bullet travels 844 meters before it hits the ground, which is a fair way. Right, part C, time of flight. Time of flight we've got to work out. Now, it's the same scenario as what we've said before. Look at what variables you now know about your vertical component, your horizontal component, initial versus final, gravity, displacements, and things like that, and pick the formula that works. We know the final velocity in y, we know the initial velocity in y, we know what gravity is, time's the only unknown left. Rearrange this guy to find for time, sub in what we know from our previous questions, and put it in your calculator, and there's your answer. 13.12 seconds. So it takes just over 13 seconds to travel that 800 odd metres that we calculated in part B. That's vertically. Right. Now, the thing that I haven't sort of mentioned here is what this 13.2 seconds, we need to specify what we're actually doing. Now, if you look at my numbers that we've used there, I've said that the final velocity in y is 0, all right? Notice that variable became that one down there, is 0. So I'm saying in y, I'm starting with this velocity that is 129 meters a second, and I'm ending at 0. So really all I'm working out in my parabola like this is from here to here. That is only half of the journey. So what this next step here is telling us is that you have to double it to get the other half of the journey. So the 13.2 seconds, to say it a bit more clearly, is how long it takes to get to the top of its trajectory, to the top of that parabola. If I double it, that's now the time to get all the way back down to the ground. So it's taking 26 seconds to then get all the way back down to the ground. All right, that's one way of working out the time of flight. Another way of working out the time of flight is basically we use the same formula, but we manipulate which particular numbers we have. And we're going to change what we're putting in for this guy here to do that. And if we look over here, notice that we've got the same magnitude, negative 129, positive 129, just in different directions. And if we do all that, we'll end up with the answer straight away, and that is calculating the entire trajectory from start to finish. Same deal, 26.2 seconds. That's how long we take to get this whole horizontal range there. We have a third example here where we can use a different formula. S is equal to ut plus a half at squared. You can do this one. However, the difference here tends to be, depending how it works out, you have a t squared in there. So often you're trying to factorize a quadratic in some scenarios there. That's why that one, sometimes we try to avoid that just because it's an extra step. But you'll get the same answer. Last one, horizontal range. There's only two formulas we've got for the x direction, and that is ux equals vx and sx equals uxt. That's literally the only two formulas we have in the horizontal direction because there is no acceleration. The velocity we start with is the velocity we end with, and our rearrangement and redoing of speed is distance over time. Plug the numbers in. Ux you got from right back in part A back here. Plug that into your formula. That's in there. The time we got from part C. Plug that in there. And what do we get? 4,000 meters is how far the bullet travels. So whilst it goes 800 meters up in the air, it's traveling horizontally 4,000 meters, and it's doing it in 26 seconds. Probably faster than you can run. Okay. Next example. Landing at a lower height than what you started off at. So in this scenario, think about this guy up here who's throwing his shot put. The projectile is leaves his hand at that high, but then has some horizontal displacement until it reaches down at the ground. So it's landing at the lower height. So we're starting with a velocity here, but we have a longer time to accelerate back down to the ground. So we know that the impact velocity is going to be larger than what we started off with because it can come back down to the ground after more acceleration. A few of my pictures there. Evel Knievel, very famous daredevil from America. Probably a little bit older than you guys, even a bit before my time. Probably ask your parents or grandparents who Evel Knievel was. Amazing guy. Did a jump over a fountain at a casino in Las Vegas. That's where he kind of made his name, and he did a lot of big daredevil trips like this, like trying to jump over the Grand Canyon and things like that. He may look familiar because he does look like a certain character in Toy Story 4. Lots of similarities there, but nothing's proven as to whether it's the same character. Anyway, let's move on. Righto, here's our example. We're landing at a lower height. We've got a cannon there at the top of the hill. We have an initial velocity it's launched at. If we looked at where the cannonball landed here, we would have the same example as the first one that we did, but no, we have longer time to accelerate back down to the ground. What have we got to find here? Cannon's fired from the edge of the cliff. The tip of the cannon is 60 metres above the surface of the sea. So we instantly know that that's what's our vertical displacement is going to be. The initial velocity of the cannonball is 88.3, so that's u, not uy or ux. You've got to work those out. That's just u. And we know our angle is 34.5 degrees to the horizontal. So what have we got to find? Time of flight. We've got to do a vector diagram to work out our impact velocities as it strikes the water. So in other words, we're going to have to find the x and y components and then resolve them back together into one vector. And the horizontal distance, so the range. So how far was this distance here? All right, let's work through that. So these particular questions, notice that the question there talks about determine is listed there in the question. Basically just means work something out after you've done a calculation. Remember, a calculation is just like numbers like maths in your calculator. This term construct is about drawing a particular diagram. That's just what the term actually means. All right, what do we know? Same deal as always. Write down what we know. We know our initial velocity, which is u. We know our vertical height, vertical displacement, and we know our angle. And obviously we know g is our negative 9.8. And we've listed the things that we need to find. So first thing we want to do is start to break it down into x and y components because they work differently. Notice what we've done here. We worked out the vertical component of the initial velocity, that is uy, and it equals u sine theta. We saw that a few episodes ago. Plug your numbers in. 88 goes in there. The 34.5 goes in there. Stick it in your calculator. It all comes out in the wash. It's traveling up at 50 meters per second. Righto. Now we can calculate the time directly from that. So what we've got here is v squared equals u squared plus 2gs, and we plug in the numbers we know and we solve for the unknown that we want. All right. So where are we here? We've got our initial velocity of 50 that came from the previous slide. 2 is just a number. G we always know is negative 9.8. And we know that the vertical displacement is 60. So like I've said before, write down all these variables, write down the one you need to know, and look at your formula book and just match them. And you'll see that one just stands out, like this scenario here. All right, we want to find Vy, the final velocity in y, in this scenario here, because we're going to do that first before we get to this next step down here. Righto, all this, so 50 squared is 2,500. Notice the plus sign is a separate term there, so you work that bit out. Add them together. Now that's giving you v squared. Get rid of the squared is a square root in there. Square root of that is 60. And obviously because it's a square root, it's plus or minus. Now we know that this object is starting on top of the hill and ending down here at the water level. So therefore the final velocity is going to be down, and we know down is negative, so therefore we're going with the negative value of 60.6, negative 60.6. Righto, knowing that, V equals U plus GT is our next formula that's in here. Plug in what we know. We know what U is. We used it up there. We know what G is because it's always the same. And T is the last unknown because this guy here was literally that one there we worked out. Plug the numbers in, put it in your calculator and work it out. Same deal every time. Write down what I know, write down what I have to find, and pick the formula that works. Notice in this scenario here, though, we wanted to find the final velocity in y. We're going to need it eventually, all right, when we start to do part B and work out that vector diagram. But we worked that out to then use this second equation in here to find the time, all right? And as a little, if you stop and pause and read this little bit here, there's the reasoning on why we just didn't do it in one step. Okay, so that tells us that it's in the air for 11.3 seconds, right? And notice that I'm starting with a positive 50, ending up with negative 60 in my velocities. My acceleration is negative 9.8, so it's giving me the entire time of flight from the top of the cliff to the water. Right, so there's our answer. It's in the air for 11.3 seconds. All right, next one, start to pull it together as a vector diagram. Now, the first bit here is determine the impact velocity, which we did before. Notice there is another way to work it out, similar to what we did up above. It's just an alternate formula that will work. So often two different formulas will work. Notice in this scenario, we didn't need that vertical displacement. Still got the same answer. It'll still work. U cos theta, we've done that before in previous episodes. That should be pretty easy for you. Give you the horizontal velocity. So initial velocity, and then the final is the same. So we've got that there. So you can start to see, we can start to construct our diagram. We've got a y final velocity, we've got an x final velocity. We can start to put it together and work out what this impact velocity is. So there's my triangle, there's my diagram. There's my x component, there's my y component. This is the one I'm starting to look for, which is going to involve finding an angle. All right, remember what we did before with those? It was just Pythagoras. Whether you do a squared equals the other ones or c squared equals the other ones, it doesn't matter. You've got two sides to a triangle. This side is obviously the same as this side here. So that one plus that one is these two. This is what you're finding out is this one. Put the numbers in, solve. That's not difficult maths at this stage of the game, so you should be able to do that one. There's no two velocities put in there, and I've resolved it back as 94.7 meters per second. Remember what we said before, 100 kilometers an hour is about 27, 28, 29 meters per second off the top of my head. So we're going very, very fast, more than 3 times that. Okay, find the angle is just your trigonometry ratios. There's my angle there. So tan is opposite over adjacent, which is the numbers I've put in there. Look at where I got the 60 and the 72 and where we ended up. Put it in your calculator and it all comes out in the wash, 39.8 degrees to the horizontal. All right, obviously down in this case. All right, that is part B. Part C, calculate the horizontal distance. Well, as we said before, there's only 2 formulas for horizontal. This one's fairly straightforward. We know what the time is. We know what the velocity is in the x direction. Plug those in. It lands 823 meters out from the base. So a fair way. All right, we're on to our last example here now, landing at a higher height like this scenario here, throwing the ball from 1.9 meters, and it's got to go through a hoop that's 3.1 meters above the ground. So what do we know? What can we say about impact speed, velocity, and angle? They're all going to change, all right? So the x and y components of our velocity here are going to change. Obviously, x doesn't change, but the y, it's had enough time to go up here to decelerate to 0 and then accelerate back to here, but it's missing this bit of time or distance to accelerate, so it's never going to reach the same velocity in the y as what we started with. So, displacement in the y direction, we say that that's 0 at time 0. So this is our 0 point here, as far as displacement goes. So at the end, well, that's the difference between these two heights here, is what my displacement is going to be in y. That's my final displacement in y, plus 1.2 meters, plus being up, remember? Right. The displacement in x, well, that's pretty straightforward because it's listed in the diagram there. That's how far away you're standing from the hoop. Angle, well, again, we've shown in the little diagram there, 60 degrees upwards. Gravity, gravity never changes. So in this sort of scenario here, check out the questions at the end of the sections and so on, often referred to as check your learning questions in the book that we use. But pretty typical thing here, we've gone through all the variables that we now know. You'll be asked various questions like, and the most common one is, what is the impact velocity over here? It involves working out your components of x and y, what they are over here, working out that using your Pythagoras to resolve your triangle, and then your trigonometry to get your angle. Very common calculation you'll have to do in this. Will you have to do it in the external exam? Absolutely. Okay, there's a couple of slides here of some extension stuff, some challenge questions. I do encourage you to go and have a look at these, pause the video and check it out. And for example, that first one there about cricket ball, is it thrown horizontally at 10 meters a second or one thrown at an angle? If I throw it that way at 10 meters per second or that way at 10 meters per second, which one's going to hit the ground faster? Have a crack at it, check it out. Think about what we've said before about objects that are pushed off a table versus thrown horizontally. A few more questions to have a go at here. This is the first one. How far will a flea go? We've given you the height that it can jump when it jumps at a 45-degree angle. Think about what you can work out from that and how you then might be able to work out the horizontal range. Check it out. Okay, a little bit more on complementary angles. They're not just ones that say nice stuff to you. Complementary angles add up to 90 degrees. It's something that you should have done in maths already. So if you look at, say, 75-degree projection versus a 15-degree projection, 75 plus 15 adds up to 90, all right? That defines them as complementary angles. Why is this significant to us? Because they have the same range. If you look at that graph there, the 75 and the 15 are complementary and they both have a horizontal range of 10 meters. The 60 and the 30 degrees do exactly the same thing. One spends a lot longer in the air and has a much longer time of flight, but the horizontal range will still be the same thing. So you just remember that. Complementary angles will have the same range and a complementary angle will add up to 90 degrees. All right, let's have a look at this example. Baseball is struck with initial speed of 20 meters per second. That's my U. At 60 degrees, so that's theta, and also at 30 degrees, theta. Assume there's no air resistance because we're in fantasy land. Determine the following for each angle: the time of flight and the horizontal range. So what do we expect? We expect that the 60-degree angle is going to spend much, much longer in the air, but the horizontal range shouldn't change. I hope you don't play baseball like those guys. Okay, first steps first, break it into its components. We know we've got an initial velocity of 20 meters a second, so we're going to break it into a y component and an x component, and that's for the 60-degree one. So that's my sine theta and my cos theta. Initial velocity is 20, so plug that in. Angle, plug that in, put it into your calculator. We can determine the time of flight with this one because we know that our vertical displacement is going to be 0, so that's going to be 0. So S is equal to ut plus half at squared gives us this scenario here. Notice how we've plugged our numbers in here and then we factorised it to take the t's out there, and then off we go with that one. Literally, that's just your middle school maths, your algebra type work to work out what's going on there. All right, if we keep going. Solve over the other side here. What do we end up with? 3.5 seconds. That's that one there. All right. Then we do exactly the same thing for the 30-degree angle. Same formula, we just changed it to 30. Same there. Same scenario there. Do exactly the same formula as we plug it into our mathematical reasoning there, and we get 2 seconds. So the one that was 30 degrees, so that was the lower angle like that, was in the air for 2 seconds, and the one that went up like that was in the air for 3.5 seconds. Very different. That's meant to be an S down there. There. All right, to calculate the range, it doesn't matter which one you use, it's going to be the same either way, and it's the same formula each time because it's exactly the same numbers. It's just different initial velocity, but it'll still work out to be exactly the same. The ball travels 35 metres. Exactly the same. That's what complementary angles tell us. That's what we expect. All right. I do encourage you to watch a few of these other videos that we've got here to extend your understanding. Of utmost importance in a lot of this stuff is doing some prac work, and the video there by Dr. Richard Walding is an awesome little prac to have a crack at. I will try and link some of those down in the comments underneath. So we've gotten to this point here where we can resolve our motion in 2 dimensions. I know this has been a bit of a long one, guys, but thanks for sticking with us. We've already ticked off most of those. Now, a couple more things I really want to talk to you about. Your data test. We typically do a data test where we analyse results of experiments and so on. Now, this particular relationship here, S is equal to U squared over G sine 2 theta, is a useful equation to remember for data tests for data analysis. It's an easy way to convert between an initial velocity and an angle to a horizontal range. You may like to look at this for an experiment that you're looking at. So perhaps you can look at range being proportional to sine 2 theta, that sort of thing. But it's an easy way to sort of convert between a few things. All right, a graph of range versus sine 2 theta will be a linearized graph. You can find the gradient from that, and the gradient is going to equal whatever's left in the equation that we haven't dealt with. And hence you can verify acceleration due to gravity from that one. It is not in the formula book, but it is useful for your data test. So you're unlikely to need it in the external exam, but I highly recommend you remember it for your data test. Okay, that brings us to the end here. There are a few little things in the textbook, the Walding textbook, that I encourage you to go and check out around some real-world physics. There's a couple of pracs to look at, and you can review the whole chapter and do some questions to make sure you understand it all. Alrighty, thanks a lot for coming.